compared to most disciplines, you can get really far self-teaching in computer science. Not necessarily even computer science, but just like programming. Like you can just build things that you want, and all it takes is one computer. Like that's all the infrastructure you need.
Today, I had the pleasure of interviewing Edward Raff. Edward is the chief data scientist at Booz Allen Hamilton, where he leads their machine learning research group. He's also a visiting professor at UMBC, where he works closely with the DREAM and IRAL labs and teaches courses in the data science department. He received his PhD in computer science from the University of Maryland, Baltimore County in 2018 while working full-time. Edward is the author of JSAT, which is a Java-based machine learning library, and is interested in applying machine learning to malware, fairness, and biometrics. He also has written the book Inside Deep Learning, where he focuses on finding the perfect balance between math and implementation of deep learning algorithms. In this episode, we learn how Edward's career in machine learning was kicked off by a happy accident while studying abroad, how machine learning is being applied to malware detection, and how a data career contracting for the government may be different from one working for a private company. I hope you enjoy the episode. Edward, thank you so much for coming on the Ken's Nearest Neighbors podcast. You have a really interesting background, especially related to your PhD, the work that you're doing with security and privacy, or, in relation to data science. And I'm just very excited to have you in to be able to talk about your fascinating experience. And you also have a very nice manner to you, and you're quite enjoyable to speak to.
Well, thank you. I'm excited to be here and to chat with you as well. And glad it's not just like a sleepy manner, it's just like putting people out into comas as I cross the countryside.
I think it's tranquil, but it's going to have lots of little smidgens of excitement as we go through across this conversation and this process here. So something that I like to do, rather than say, hey, tell me about yourself, I really like to start every interview where I'm asking how you first got interested in data. Was it one pivotal moment where you're like, wow, this light bulb, I love this? Or was it this slow progression where you found yourself and you made this your home in this field?
For me, it was a complete accident and like accidental discovery. And then I loved it and was like, oh yes, this is it. So I knew early on that I wanted to do something with computers. I loved computers. Was in a computer science program, doing like an accelerated master's, and just like every credit I could was computer science. And I was also doing a semester abroad out of a convoluted scheme to get out of doing a foreign language. So if you did a semester abroad, you could satisfy that requirement. So I went to England because it's a completely different language there. Lots of communication problems. And
such confusion.
There was confusion. There was confusion about like what classes counted for what. So I had like looked up one of the universities that they have like on the pre-approved list, and I was looking at the computer science classes. And so like Purdue was like 100, 200, 300, 400 was like freshman, sophomore, junior, senior level classes. And so it was a semester abroad in my junior year. So I was going, okay, I would look for 300 level classes. And I went to the University of East Anglia, and the classes went from like 0 level, 1 level, 2 level, 3 level. So I was like, oh, it's like a computer science thing. They're counting from 0. Cool, I like it. And so I selected some like 200 level classes, and okay, that'd be good. I was completely wrong. The 0 level classes are like this weird mix of like AP high school kind of thing. Like you would do that in your senior year of high school in the British system. And then like if you like took some other APs, like you'd have to go back and take that 0 level. So the 200 level classes, like I got there and I was meeting with the professors there and like, oh yeah, you can't take these. These are remedial for you. Like you need a 3 level class. I was like, oh, damn. So
computer
just
science
like,
counting strikes again.
Yeah, it was bad. So literally like the first day there, I was being told your entire schedule was wrong and you need to like somehow get new classes to take that you haven't already taken at Purdue, that you know enough to actually like take, that you have the like the prereqs, and also get it approved like immediately in another country. And that what ended up happening is I ended up getting 2 classes there in machine learning and information retrieval. And thank God I screwed up counting from 0 and 1, because like I fell in love immediately. I really enjoyed the classes, and it was just sort of like this perfect mix for me of like lots of computer sciencey stuff and programming, but also being able to like build tools that are helpful to lots of people. Like I really enjoy building tools. And so like I was really into compilers for a while. Like that's a tool for just nerds. Like no one else wants a compiler. It's just like a subset of computer scientists. But machine learning, you're building tools that like could be useful to almost any application or domain or field or specialty, and that was really appealing to me. So that's sort of how I got into it. And from that point forward, I was just like all in. Like every class I can take, I'm gonna like gear it to somehow benefit me knowing more about machine learning and data science.
That's awesome. Well, I had a couple friends that tried to skirt a language requirement because they said, well, I know Python, I know Java, I know Scala, I know C, I know JavaScript, and the administrations did not really take that well to that. But I think it worked. I'm really glad to hear that it worked out that way. I think that a surprising number of people fall into this field because of sort of happy accidents. I mean, my experience is a very different type of accident, but I was looking to solve one problem and I happened on some more advanced analytic techniques, and I wouldn't have jumped to those initially. I wouldn't have thought, oh, I can solve golf performance with some different types of modeling techniques. But eventually I got there and I was like, oh my goodness, like I probably wouldn't have stumbled on this in any other way than the route that I went on. But thank goodness I did. And that's really exciting. I'd like to maybe even rewind back a little further than that and understand what got you so excited about computers to begin with. Is it just that as a kid you were like always playing computer games, or was it that just the way that they work, the system, like creating systems and structures and coding is something that's like attuned to how your brain works?
I'm not entirely sure. And definitely a big part of it was my dad, who was a very technical guy. He used to be a mechanical engineer. He actually changed careers. He decided he was tired of being an engineer. He became a medical doctor after. But he, like when he learned to program, it was punch cards. So that was like all the programming he knew. And he helped me explore a lot of different sort of like technical interests. Like I remember a science fair, I made a really janky electric motor that would like fluctuate between like 2 and 80 amps, just because it was literally made of like Legos, wire, and like hot glued to a plank of wood, which probably wasn't the best scaffolding to build like an piece of electronics with enough energy in it to like actually hurt you, but that's what we did. And so he sort of helped me explore a lot of different sort of like science things, and eventually it was just sort of like computers are like in this weird technical domain thing that I had some just basic level of interest in, and I wanted to learn more about that and do more. And it just sort of slowly like built up over time. Like I liked it more and more, and so I just sort of kept dogpiling in that area. It was also something, I think part of how I fell into it, once I started to learn a little bit of programming with some help, is that compared to most disciplines, you can get really far self-teaching in computer science, not necessarily even computer science, but just like programming. Like you can just build things that you want, and all it takes is one computer. Like that's all the infrastructure you need to go a very long distance in learning how to develop and write code. And especially early on, so much of it like doesn't matter too, like knowing computer science concepts like dictionaries and sets and lists and big O, like that's all definitely helpful. But there's so much early on that's just like you getting used to like programming and converting like I want to do this to very pedantic instructions. That's just practice and being able to get that in really early on in life. That is, I feel like much harder for most other things. Like if you're really into like biology, you can't just like go grab dead frogs and dissect them. Like that's creepy.
I mean, you could, but
like,
probably
yeah, it has to happen in like a structured school environment where it's planned. Yeah. Or like if you're really into chemistry, like you can't just like give a kid a credit card and like access to Amazon and go order some chemicals online and mix them together. What's a hood vent? Just go play outside.
What are goggles? Who needs those?
Yeah, what are goggles?
Well, I really
very incremental.
I really like that. I think that's something I'm constantly thinking about is what gets people interested in certain fields and domains and what makes them stick to them. And I forget who said it. There's countless books out there that talk about interest and passion, but paired with affinity. And I think in computer science and well, probably more so in programming, it's not that hard to get a reasonable amount of affinity, right? If you're programming when you're 13 or 14 years old, you're going to have a tremendous amount of affinity. You're going to be good at it compared to every other 13-year-old because there's so few people doing it. And, you know, that's a feedback loop. People are like, wow, you're doing this at this age. And it feeds into these other things. And it's incredible how those two forces, the passion and the affinity, feed off of each other. I know that, you know, I basically took, I've told the story a lot, but I changed majors a lot when I was in undergrad. I think I had 6 different majors over the course of my career. I obviously honed it in by the end and stuff, but because of that, I took 4 different intro statistics courses. So there's like research methods for psychology intro, health exercise science, business statistics, and then just like a gen ed statistics course. And I saw it enough that I developed an affinity for statistics. Like if anyone takes a basic statistics course 4 times, they should probably be at least okay at statistics by the end. But, you know, I also realized, hey, this is something I can apply to my life probably after the 2nd or 3rd class that I took. And those things matched up and I got really into it. I said, wow, this is something that I can use. This is something that I've become pretty good at because I've spent so much time doing it relative to my peers. And I think it's so cool that you were able to find that at a younger age, and the systems, whether it's reinforcement from your father or the availability of these resources relative to other things, that this field is so beautiful, data science, statistics, whatever it is, because you can develop that affinity now at any age, whatever it is. There's just so many resources. There's so many ways that you can find a way for you to be good at any specific domain, again, within the technology space. I'd love to kind of dive a bit more. We've really worn out your early years and your education, but I'd love to hear how you transitioned from your courses, doing work in academia, to landing a job in the data domain, and what that experience was like for you.
Yeah, I mean, landing the job, I benefited a lot from Purdue having a really like healthy career fair and sort of corporate recruiting. I don't want to call it culture, but like it's a lot of companies come to recruit from Purdue, and there's like a huge career fair. It's like it was like 125 different companies showing up, and really just getting like the opportunity to talk with people from different companies and sort of say like, hey, my name's Edward. Here's what I'm doing. Here's what I'm interested in. and eventually finding Booz Allen for my first full-time adult job out of school, that was interested in me and my background. And they said, like, yeah, we've got machine learning stuff. You don't have to have a PhD to start doing it, which was one of my big concerns. And it just sort of fell out by happenstance. I wasn't looking for Booz Allen in particular. They found me, but glad they did.
And what were some of the mechanisms that, obviously you talked about the job fair, but, did you have research published? Did you have things that were out there that would help Booz Allen to be able to find you as well?
Yeah, I mean, I didn't have research at the time. At the time, actually, something I had started doing back in high school was basically just writing stupidly large code projects over multiple years. So like in high school, it started out with writing my own graphing calculator because I would take notes on my computer and I wanted to like plot whatever equation we were talking about in math class and like copy it into OneNote. And so I wrote my own graphing calculator and plotted it, and then like I would plot like e to the x and it would go up and then it would overflow and go negative. I was like, what is this? This is broken. I learned, oh, it's not quite broken. It's just like, that's how floating point works. And so it like turned into like an arbitrary precision math library. It went on for 4 years. And I wrote a stupid amount of code for that. And then when I learned about machine learning, I was like, oh, okay, I want to do that. So I started writing my own machine learning library. Just because I'm one of the only brain dead people who likes Java, apparently. Like, I really enjoy Java. And the only library at the time really was Weka for machine learning in Java. And I didn't like it, just the way Weka was set up didn't jive with me mentally and how I thought about it. So I was like, all right, I'll just write my own. And so I just started writing algorithm after algorithm, sort of implementing it all from scratch. And so that was really part of how I got my job at Booz Allen. Was I just sort of like was talking with the person who was there to recruit was technical, and I was telling them about my side project implementing support vector machines and linear algebra and all the sort of stuff I needed to be able to run any of these algorithms. And he was like, cool, you want a job? I was like, yes, I like money.
I mean, I love that. That's something I'm constantly reinforcing, is that if you're building a portfolio, if you're working on things you're interested in, I mean, other people are interested in things that you're building. I mean, the best way to show that you have aptitude is to build something. It's not to tell people that you've built something, right? It's to say, hey, like, I have this GitHub repo, like, check it out. Yeah, this is what I do in my free time. Like, I think that's maybe a step beyond what most people are doing for. I mean, you obviously weren't even doing it to land a job. You were doing it because you enjoyed it. And yep. I think that a lot of people, I mean, they can find a way to do things that they enjoy, but they can also use that as like a really positive thing for their career employability.
Another thing as well, especially for something like machine learning, I feel like it flows much easier if you pick something that's just like, you don't necessarily pick a machine learning project, but you pick like an actual problem you want to like solve or something you're interested in. That's something, especially with like when I teach my sort of data science or deep learning class, and I'll usually do a course project. People say like, well, what should I do for my project? It's like, no. Like, tell me,
figure it out.
What are you interested in? It's like, I'm interested in machine learning. It's like, no, I'm not talking about machine learning. Like, what problems are you interested in? And like, what's annoying you in your life? And we're like, well, I can never find like new books that I want to read. It's like, okay, that's a machine learning problem there. That's information retrieval. That's recommender systems. Like, okay, let's build a data set on like what books you do and don't like and which ones you read and like who the authors are. Like, let's start thinking about how we would solve that problem. I think that helps. I think it like drives people to really learn the techniques, because they're actually trying to solve something and not just trying to like learn how to turn the crank, but they're trying to figure out what fits for their needs. And it's also much more motivating to keep working on something when you actually care about the output, rather than just like trying to get like a sticker to show like, I did it.
No, I could not agree more. That's something that makes me really happy that you brought that up, because in comments, in questions, in emails, and LinkedIn messages, I am constantly asked probably at least 10 times a week, hey, what project should I do? And I'm never going to say, well, I'm obviously never going to say like, oh, do Titanic, do Mince, do Iris data set, right? I mean, that's not going to differentiate you from the pack at all. What I do say is like, look, find a regression problem, find a classification problem, find a clustering problem, find a reinforcement learning problem. The problem is the key word. And then, that can help you niche down, right? If you're like, well, I want to classify something. Okay, what things do I need to classify in my life? Maybe it's like on YouTube, I have comments and I want to classify spam and not spam, or positive and negative comments. Great. Like that's an easy solution. But all of machine learning, our focus is on solving problems. And you should start there and work your way back and figure out what type of problem it is, and figure out what type of algorithm you're using to not solve that problem, but to optimize for that problem. And everyone is focused on it the other way. Is, oh, I want to show that I know machine learning. What data should I use? What all of these things? And it's like, no, like none of this work, unless you're like very, very, like in a very, very specific research scientist or academic role. All of the work is about what you can do with the data that is, it's problem specific, subject specific, and I'm really glad that you're reinforcing that message there.
And I think it also helps when it comes to like interviewing for the job. Like I do interviews with tons of people, and there's always someone who like they list their class project on their resume. And they can talk about it. Maybe sometimes it's an interesting class project, but sort of intrinsically limited scope of like what you could do for a course project. And like whether you think it should or shouldn't, like seeing people with like passion helps drive like, oh, we like interest in hiring that person, like, oh, they really like know their stuff. And also helps you like remember it when you're talking to someone months later, if it's something you really like worked hard on and cared about, that all these details. And it's also when it's something you care about, you think a lot more about like, well, what would I do next, or what problems are there still here? And that comes through a lot more and shows a lot more mental ability to work through and really understand what is or is what does or does not make a complete solution. That's something like when I interview people, I'll just ask them about like whether it's a project or prior work or whatever. I'll just keep asking them to go deeper, like rather than like, I don't want to do some weird like coding question or like puzzlers or teasers. Like those aren't great, especially like if someone just doesn't know that like one trick in order to solve your puzzle. That's also like it's an interview, like it's stressful for the person trying to get a job. But if you're just like asking someone about their interests that happen to be related to the technical goal of the job, I find that's a really good way both to learn what someone knows and also for you to sort of express and show the depth of what you can do.
Yeah, again, I could not agree more. The further you go down that rabbit hole, honestly, the better. I mean, if we're putting together projects that we care about, it shows that your focus in that machine learning problem or in that project is stakeholder focused, right? If I'm building a project for myself, there's going to be someone that's using it. It's going to be me. I mean, if I'm building a project for someone else, also great. Like the goal of any algorithm, the goal of any product we make with machine learning or data science is for someone to use it or some system to integrate it. And the more people that are using that system, even if it's just you, if someone is using it, to me that is like this like binary, like this is a great thing, this is a great project, or this is not a great project. Like that is, I wouldn't say that's like the only criteria I use for evaluating candidates, but that's something if they're really thinking about, okay, who's the end user? If it's me, great. How do I optimize for maximizing whatever they want to, whatever I want to get out of this? That is a major, major differentiator in my opinion.
Yep, 100%.
Awesome. So you talked about how at Booz Allen, you did not need a PhD to get started, but you did end up pursuing a PhD while you were working.
Yep.
I would love to hear about what that experience was like. I would imagine it was, I did my master's degree full-time while I was working full-time. And I can't say that it was like the best couple years of my life in terms of work-life balance. I can't imagine what it was like doing something that was even perhaps more advanced or more dedicated course of study.
And there was definitely a lot of luck involved. Because I didn't need the PhD to get started. I sort of got started into a research-oriented applied role with just my master's, and was working on some interesting stuff. And the client I was supporting was located at University of Maryland, Baltimore County is the school I went to, it's UMBC. The client side I was reporting to every day was in that school's research park. Like literally, it's a 12-minute walk from the building where I would work and get a Subway sandwich every day, and then 12 minutes to the computer science building on campus. And I was in a really good place where I went to my client, I went to my Booz Allen leadership, and we said, like, I still have this like weird irrational desire to get a PhD. Because if you sort out like all the reasons to get a PhD, there's not a lot of good ones. I still wanted to get a PhD, and I think the work that I'm doing for my clients is publishable. I asked them permission, like, could I publish the work that we're going to do, which is part of your goal. If I got into UMBC, would you let me sort of stick the UMBC affiliation on it and sort of like double dip and get sort of credit for school? Because you have to publish to get a PhD. That's part of the goal. And they were on board with it, and they understood that it was sort of a mutually beneficial setup. And my leadership in Booz Allen supported it, and so I was in a really good space where, like, if I had to go take a class during the middle of the day, I sort of made sure my people at work knew, like, hey, I'm blocked out during these time periods. I would just walk from work to class, take my class, walk back. And then, like, my day job was making progress towards my research goals and my PhD, because we were doing cool work that was publishable. So that significantly reduced the amount of time that I had to spend sort of outside of work doing additional research. So I was very, very fortunate and lucky to get that situation. And that's primarily how I was able to sort of get my PhD done while working full time as well. Which was still a lot of work, but it made it much easier. And then that's something I've been trying to support other people in as well, is trying to replicate my good fortune with hopefully less luck required for future batches of people that want to do the same thing.
Well, I mean, I think that there's a great value add for universities, value add for individual people who are looking to pursue like more research focused careers. I mean, if you're looking at who's employing most PhDs now, I mean, it's still universities, but a large contingent are going to Google, to Facebook, to these companies that are really focused on AI research. And if you had a hybrid program where someone could work in research in industry while they were doing their PhD, that'd probably make the transition a lot smoother if people did want to work at a private company and do research at, well, I forgot NVIDIA as well. That's another big one. And you know, a partner of theirs, so I probably should have mentioned that first. So I hope no one heard that. No, I'm just kidding. But you know, to me, that's something that, wow, there's a big market there. I mean, I would even, I probably will not at this point in my life, but that's something we've talked before. Is like I'd experiment with, hey, like that's a pretty fascinating proposition. It'd be nice to extend my learning further if I could do that while feeling like I wasn't falling behind in some of the other areas of my life. That's kind of a match made in heaven, which is pretty fascinating.
Yeah, I really enjoyed it. And I agree. There's a lot of mutually beneficial stuff that comes out of it. There's some stuff like when Booz Allen has tuition reimbursement. So I paid almost nothing for my PhD. There was one weird, like, goofy year where, for whatever reason, I had lived in Maryland for several years at that point in time, but I was somehow an out-of-state student. I don't ask me to explain how, but apparently I was out of state for 1 year while in state. But I paid almost nothing out of pocket for it. And then that also means, like, my advisor doesn't have to, like, find grant money for me. So there's not this sort of, like, pressure of doing a potentially unrelated research project. They don't have to worry about, like, feeding me and clothing me and getting me healthcare and all that stuff that a professor sort of kind of indirectly does. And then, I mean, my research itself, like, had a very good focus and motivation. There was like, I have this problem at work to solve. That's the motivation. Like, I remember one of the people on my committee is like, well, like, does this research, like, have a practical impact? Do people care? It's like, yes, this has been my day job.
They're literally paying me for this.
It's also, I think, I remember when I was doing normal, like, undergrad full time, and I was definitely more fortunate in my life and upbringing than most, but still a lot of ramen and cheap living and not having all the benefits and luxuries that I have now as sort of a more complete adult with a full job and income. And that was actually one of my big worries. I had two big worries going back for a PhD full time. One was that I wouldn't be able to, like, give up, like, the lifestyle that I can afford with a full-time income rather than zero income, because that's a pretty big gap.
Yeah.
And then my other worry, because a lot of people don't finish a PhD, and normally if you go into a PhD program, you decide, like, you know what, this isn't for me. You academics are weird. You have perverse incentives. No one knows how to communicate. I'm out of here. You can sort of bow out with a master's degree. So you get something, like, along the way. I already had my master's in computer science. I couldn't bow out with another master's in computer science. I'd look like an idiot. So I was very, like, if I do this, I have to be able to finish it. I don't want to have two masters in computer science.
That is very, very. Can you touch a little bit on what some of the topics of your research has been in the past? If there's anything sensitive work related, obviously no pressure to talk about those things, but I'd be fascinated to hear, you know, what type of research you're doing during your PhD.
Yeah, most of my research has been around machine learning for malware detection. So something comes in, it's an executable or whatever it happens to be, and you want to know, like, is this dangerous? If I let it run, it's going to destroy the world, so, like, stop it. Or no, it's benign, it's safe, you can let it run, don't worry about it. Which is an intrinsically important problem. None of us like malware, and especially with the increasing prevalence of ransomware, is pretty aggravating and destructive to people. And especially there's been instances of ransomware like getting into hospital equipment and bricking like medical equipment, which is now actually a real life physical hazard posed by malware with unfortunately increasing regularity. And it's an interesting space because it's sort of this combination of two really different depths of a potential computer science education. Like there's very, very deep depth on the system side. Like how does the malware like connect to the internet, and how does it exploit DNS, or how does it exploit the x86 instruction set to do something you didn't expect, or how does it get privilege escalation to run that and alter files that it shouldn't be able to alter. So there's a lot of really deep system stuff, and it's weird system stuff because you can't assume like, well, this will work, because part of the whole point is, well, there might be a bug that it's exploiting. So you have to kind of handle this to be really cliche box of worms of what malware could do. And then on the other side, you have sort of the depth of like math and machine learning. And usually people don't go super deep on both like the math and the system stuff. People tend to lean more towards one or the other. So there's this really challenging intersection of knowing, or at least partially understanding, both of these things. And a whole part of my, well, really the whole goal of my thesis, and it's still a very big theme in the research I do today, is how much human effort can we eliminate from this process? Because currently the best and most accurate solutions have sort of handcrafted domain knowledge features. We haven't reached like the ImageNet moment. Like deep learning has drank all the milkshakes in terms of computer vision, NLP, sometimes columnar data. Like in those cases, like, okay, like don't handcraft, just let the deep learning algorithm sort of figure out what it wants. For cybersecurity, not the case. Handcrafted features still far superior in terms of accuracy. But they're also brittle. So the malware author, like if you build your system, it detects the malware. Malware author notices that they're no longer getting ransom money. So then they change their malware until they get through whatever you're doing. So it's constantly evolving. That means your feature engineering never ends. And it's really expensive feature engineering because you can't just, one, parsing is hard. The Windows PE spec doesn't match what the like Microsoft Windows Loader actually does. And then even then, again, there's like malware's constantly exploiting weird bugs and things. So you can really not reliably parse executables and know what you're going to get. And I've done stuff where like you run 3 different parsers and they all give you a different answer for like what's in this executable file. So my goal is like, well, could I get machine learning to work from raw bytes? Like literally just feed into the algorithm, here is a sequence of bytes, that's all I'm telling you, you figure it out. Which is hard for a number of reasons. It's got like a weird, like a big data set is like hundreds of gigabytes, and that would be like millions of files. And this is a domain where you could have a single 200 megabyte executable is not that outlandish. That's actually kind of normal. But if you think about it, that's one 200 megabyte data point. There's a lot of stuff that you can pack into 200 megabytes.
Yeah, no kidding.
And to identify like, well, is it all 200 megabytes of malware and evil, or is it like one teeny tiny portion that does the malicious stuff? And and like executable code, and it's like by definition, it's Turing complete. Like it can do anything. And you're telling the algorithm, one, you can't perfectly predict it because of the halting problem. Like you need to actually run it in order to get a definitive answer of what happens. And even then, there's like asterisks when you get into like real life malware. It's like, okay, you're the halting problem solving way, but also you don't know that it's code yet. Like it's just raw bytes. So the malware or your machine learning model has to somehow on its own figure out like, okay, where does the code actually begin, and what am I going to, how do I parse out the code and understand what's happening? There's just a huge amount of complexity of what you would need to get the algorithm to understand in order to make any progress on this problem. But that's the approach I chose to take because I'm not smart enough to reverse engineer anything. And sort of kept hammering on that until I actually started to make some progress. So that's kind of the main research theme I've had for my PhD and for past it as well.
Well, I mean, it's fascinating in terms of the types of questions and the impact that it can have, and the image stuff you're talking about, the NLP stuff you were talking about before. It's a lot easier to conceptualize, and the problems are also a lot more well defined, as you alluded to. And I'm wondering, I mean, is that agnostic of operating system? Is that something that that
was part of the motivation? Was that if you come to me, maybe in 2 years, Nokia has like arisen as a new platform. They've got like a new OS. They've invented some completely new. And so there's a whole new platform that we need to now create an antivirus for, because there's going to be malware for it. There's malware for every possible electronic thing you could think of. So, okay, some new platform is going to eventually come along. Well, okay, we need a malware detector for it. Like, oh, okay, what's the lag time for like you to get a bunch of reverse engineers and experts to understand this new platform, understand its vulnerabilities, develop a feature set, collect all the data, train up a model, and get that working? Like you're talking about years and tons of people's effort. But if you have a machine learning approach that has no assumptions baked in, like it just works from raw bytes, and you still need to get the data, but you can turn, like as soon as you get data, you can turn around a model. So that was one of the motivations, was to have a much smaller lag time between like, I need something and you can have something. It might not be the best something, but it's available. There's also a lot of interesting forensic cases where there's no other alternative. So like if you're tracking some malware that's in your network or something, and the connection cuts off for whatever reason, so you have a partial file fragment left over, you can't parse it, it's incomplete. You can't run it, it's incomplete. The only option you have is to use something that can just work from raw bytes and does not need to parse anything, because you don't have enough of the file to parse. Or if you have a corrupted hard drive, you might not, the header might not be intact. There might be literal gaps in the file that you can't parse because they're just missing. So you can't use any of these more sophisticated tools, in which case we have something that you can use and you can run it and figure things out. There's also one of the things that we've got a lot of utility out of our research in this approach thus far is being really ridiculous fast. Because parsing, like it's a non-trivial operation. It takes time. But imagine if you have a firewall and you've got terabytes of traffic going through this firewall every day, and you want to be like live scanning things going through into your network, you do not have time to parse everything coming in and rebuild it and figure out what it is. But if you don't need to do any of that parsing, if you have a model that can just literally run on the raw bytes coming in and quickly get you an answer, that gets you something you can start acting on. And that can feed into other processes. Maybe you grab that just one piece and say, oh, let's rebuild that one piece. And we'll slow that down, or we'll pause that, or we'll quarantine it for a bit, just so that we can check that one piece more thoroughly. With something that's more expensive and more accurate, but would be too slow to run on the whole fire hose of everything coming in. That's where we've gotten a lot of utility out of the work we've done thus far, is fitting those situations that are very resource constrained. Sorry, I'm kind of like just sort of on the zone of just like talking about the things that I think about.
No, I love this. This is fascinating to me. I mean, this is something I've never really, obviously never personally explored. I'm sure everyone listening, this is completely or fairly novel to them. And, you know, I have some questions about kind of the broader like scope of malware to begin with. Are there ways that people who are creating this are also using machine learning? It's also one of these problems where, you know, you're always chasing, and it seems like there's so much more flexibility for what the people who are creating this are doing in terms of like randomness and trying things based on volume, compared to what you're trying to do, which is scale something that's more generalizable. I mean, that's always a very difficult problem to tackle, right? Is that you're always chasing, and, you know, hopefully you can get something that's built to scale, but they're building things that are focused on optimizing or focusing on targeting individual, very small, like idiosyncrasies. So you're going general, they're going specific constantly. And that battle is just such a fascinating, like, conceptual thing in my mind.
Yeah, that's actually, that alludes to something that I think a lot of the academic work in this space loses track of. You can get very focused in on like, well, what could go, like what could go wrong? What could you fail to get? What could the adversary do to circumvent you and to subvert you and to succeed despite your efforts and time? And the answer is almost always they can't defeat you. But that does not mean that the work is useless. Especially in malware, there's sort of this huge spectrum of things that are just like super lazy, and the malware authors are just blasting it off and hoping that people are dumb or
numbers game. Yeah,
they're just playing a numbers game. And then there's script kiddies who are just like, they don't really know what they're doing. They just like downloaded this thing online, or they learned about poison ivy, and it's this little like point and click interface to make malware and sending it to like their friends, or doing whatever stupidity that they're getting into.
Don't give the community any ideas.
That's another, like, there's a lot of low hanging fruit that still like needs to be stopped. Is still a problem. And then there's like all the way on the extreme end of like malware written by entire like criminal organizations that like can have a literal team of people working on something and spending time on it and reverse engineering it. And like when you get into some of the absurdities of like what malware, so like I'll give you two like high-end examples on like what malware could do that's like just kind of crazy if they're trying to like accomplish their goal, and then like just some of the stupid stuff I've seen. So like there's malware that will literally like have its own instruction set in order to make it more difficult to reverse engineer. And so they have their own virtual machine, like kind of similar to the Java virtual machine, except it's their own like custom one. And every time that the malware like propagates or they compile and send out a new version, it will generate a new randomized instruction set with a new virtual machine. So that every single time you're trying to look at this malware, it looks completely different. And it's got a whole new instruction set that you have to reverse engineer every single time, which is just like, that's currently a really annoying thing to people in this space today. Because there are no good tools for dealing with this stupidity right now. And there's other malware. So like if one of the more expensive techniques that you would use, especially if you got something annoying like this VM wrapped craziness, is to run it inside of a virtual machine. And so you observe like what is its actual behavior instead of trying to look for properties. And that's very intuitive because like, oh, if you see it like starts encrypting the entire file system, you know, oh, okay, this is definitely bad. Just like shut it down. And then it doesn't matter that you couldn't sort of like figure out like how to look at it because you just sort of saw what it did. That has two problems. One, it's very expensive to just run things inside a VM. And then malware can detect that it's inside a virtual machine and alter its behavior. So it may not operate the same way inside of a virtual machine as it does on a regular like desktop or laptop. And there are even virtual machine escapes where there are flaws in the virtual machine software that the malware can then exit the VM and take hold in the host operating system. So you can potentially have a situation where like you were trying to run the malware safely inside of a virtual machine, and in doing so, you have infected yourself. So that's like stuff on some of the higher end of just like annoying stuff that you might have to deal with and can make it like, well, yeah, if they put in that level of effort, like I'm not necessarily going to catch that. But at the same time, I've seen malware that is literally like, so inside an executable, there's different section names for the different kinds of content. So there's a .data section where you might store like some images or a .code or .text for where the actual code is. There's other different uncommon section names. And I've seen malware that literally renamed the code section to .virus, which was like,
thanks.
Okay, I believe you. I'll just quarantine you now. I've seen malware with like literal like poems about their like weird manifestos about like why they're doing this or why people deserve it or whatever. Like there's all sorts of dumb stuff that you see too. So it's this sort of huge spectrum of sophistication or lack thereof that we're dealing with when we're talking about malware. So yeah, even though there's always like this little bit you're just not going to get, the more you can, the more you're still helping people. Sorry, that was kind of a...
No, I loved it. That's a, again, like a topic, like nuance related to that field that I have, that is fascinating to me because I've literally no experience with it. And it's very cool to see that, hey, I mean, machine learning, data science, whatever you might choose to call it, it's being applied in hopefully preventing those things. And the beauty of this field is that algorithms can be generalizable rather than specific, you know, more decision tree like approaches. And I mean, you talked about NP complete problems previously, and like when we have problems like that, estimating them is essentially the most effective way to get results in a reasonable amount of time. And so the more complex the problem, in my mind, a lot of the times the more valuable machine learning, AI, data science is going to be. And so it's really cool to see that, wow, this is a complex problem with such a range in value in complexity of the individual malware that's coming in. You know, what's the best solution here? You're working on it, right? Or yeah. You know, so I love that idea, and I definitely want to learn more about this. I don't know if you have any articles that you've written or research you've done. I'd love to share that with with people in the chat below, not in the chat, in the description below the video, because at least I would guarantee, guarantee is a bit far. I would bet you that someone listens to this and they say like, wow, this is an area I want to focus on. I want to research more on this. I want to understand this, because
oh, sorry, go ahead.
No, this is just a subfield within data science that I would imagine is going to be, there's a huge demand for people to work on this stuff. And yeah. I would imagine, I don't think I've heard too many people talking about it with the detail that you're talking in about what's going on in that space.
Well, and I only occupy really a small world of like the intersection of cybersecurity and machine learning stuff. There's a lot more to it than just the malware itself. And I wrote a survey paper last year specifically on like challenges for like malware, for Microsoft malware detection with machine learning, where I sort of tried to just like brain dump as much as I could on like what I had read in this space and like what people have tried. There's also just a lot of interesting fundamental machine learning problems, especially around data sharing, because like if people want to share malware with each other and build like a data set of malware, that's fine, that's easy. There's websites actually dedicated to that. But if you want to build a good like benign data set, because like all things machine learning like starts with your data and it's got to be as good as you can get. Getting good benign data is really hard because benign data doesn't self-propagate like malware does. Like malware is trying to get out there. And so it's pretty easy to get lots of malware. I mean, you can literally, like you could just take a copy of Windows 95, connect it to the internet, and you will get malware. Like it will come find your box and get on it. You don't have to ask. But benign things don't do that. And if you like share malware with someone else, no malware author is going to like come raise their hand and be like, hey, that's my malware. You're violating my copyright by sharing that without permission. Because like the FBI is just going to show up and be like, okay, we're arresting you for distributing malware. But if it's just a benign application, like that's some companies or persons like intellectual property, you do not have I apologize, English is my first language. You do not have the rights to just share that file. So how do you build like a nice big corpus? So it's how do we solve these kinds of problems are really challenging machine learning problems that are also deeply tied with this very applied practice in space.
Well, I find that the more complex the problem, the more questions we have compared to answers. So it seems to fit, right? Switching gears a little bit, I would really like to hear your experience working as a consultant to government organizations. I mean, that's generally, I believe Booz Allen has a huge public sector contracting practice. And I'd like to understand how, what that experience is like. I would imagine you wouldn't have access to some of the data that you have if you weren't in that type of role. You wouldn't be working on similar problems to what you're working on now if you weren't in that type of role. I just want to get a lay of the land for, hey, what is this type of work like? Where you're working closely with the government, perhaps compared to, maybe I can add more context on what the private sector work is like. But just your experience there. I mean, we've talked, and you clearly enjoy what you're doing. So I'd love to share more opportunities with more people to realize that, hey, like you can do data working for the public sector.
Yeah, I mean, I definitely enjoy my job. I can't name clients because I don't have their permission in advance. I mean, some things are just not different. Like you have bureaucracy and structural organizations and resource constraints and budget constraints that exist in any large organization, whether that be the government or any company on earth, are going to dictate like, well, okay, what do you have access to? Like, okay, do you have the money to buy data or get data labeled, or do you have your own internal database that you're just going to pull from? Those things are kind of the same everywhere. But there's other parts, I think that's really sort of like the nature of what success means that can be different. And a lot of work for like a public company is intrinsically sort of profit motivated. Like, we want to show more ads, or we want more people to click the ads, or we want people to stay on the website longer because that correlates with people buying more. There's sort of like a very natural common theme amongst all these companies in terms of some of the ways that the machine learning projects go. But that and there's projects like that within the government. You want to save money, you want to save the taxpayers money. There's also projects where sort of the goal is just like more public benefit oriented. So like, okay, we want to, I'm just going to make problems up just to keep people happy. But like, maybe we want to figure out like where's the dirty water or lead pipes that need to be replaced. What kind of chemical interactions should we be looking at for like some drug development or something, or for some cancer research, or like just how do we stop more malware, or how do we I'm having trouble on this last one, coming up with something on the spot, but it's more just sort of like the nature of like what the goals and successes are not to be pejorative of people working for a private company, but sometimes they're more sort of intrinsically motivated goods. Like I did not get into this job space because like I wanted to do good for America, or like I felt a calling. I just really liked machine learning, and I was told they had cool machine learning work for me. But it is something that's actually like I found a lot of pride and sort of like fulfillment in, is that a lot of my work like really tackles things that are public goods and are often things that are difficult to like motivate from just like a for-profit perspective. So
I think that. Go ahead.
Oh, sorry. Go ahead.
Oh, I think that's a really cool thing in general, is that it can be profit motivated in private sector, but you're also adhering and doing things for stakeholders in a company. And stakeholders in the company, they generally want things to happen fast. They want to make their money. They don't want to do whatever. And in a lot of ways, that can be aligned with creating value for people, but a lot of times it also isn't. I think that there's two things that are, from what I understand, are probably a little different when you're working for the government, is that timelines can be a little bit broader. And that's generally a good thing for data science, because you can experiment a lot more. You can create really valuable products when you're not like, oh, I have to make an iteration of this model by Friday in the sprint and whatever that might be. And also, just like that, the stakeholders are the are U.S. citizens, basically, right? For the most part, and that kind of change in paradigm, that idea that, hey, we're creating value for technically yourself too as a U.S. citizen.
Very self-serving.
but that's like a different way to look at a problem. That's a different way to incentivize, and it does have implications on the type of research and the type of work and how the work is done. I mean, to say like those are good things or bad things, they're just different. But I would imagine that working for a private sector versus working for public sector, depending on your own goals and issues, the type of work you want to do, it could be a different journey for you'd have to match it to your own personality and your ambitions and goals.
Oh, yeah, and again, I think it's more just sort of the themes of like directions that projects take. Again, like a lot of machine learning work in I'm not trying to say all like public sector projects all follow the same recipe, but there's a lot more like common machine learning projects that are very similar across lots of different public companies because they all sort of have the same motivation and need. Like, okay, almost every company does some level of advertising. They want their advertising to be as effective as possible. So they all end up pursuing some form of solution around what is my return on investment for marketing to this individual. And some do it in-house, some outsource it. But it's just like a lot of people work on that because it's an intrinsically profit motivated thing that an intrinsically profit motivated organization will work on. And I'm not calling it good or bad. It's just sort of like a common trend. But there's common trends in government work on the nature of projects that you don't see as much otherwise because like who but the government would work on that problem.
Very true. Interesting. So that's the majority of my questions. I do want to ask you a bit more about your book, Inside Deep Learning, and what was your onus for writing that. I'd love to learn more about it, and feel free to hype it up, talk about it. It's interesting. I always am interested. Like I've been asked to write a book, and I'm like, oh, that's a lot of work. I don't know if I want to do that. But with the PhD and then the book, it seems like you might be just a bit of a glutton for punishment. So.
There is definitely some level of unchecked masochism involved in writing the book. I like teaching as a part of my role that I really enjoy is like mentoring junior staff and students when I'm teaching for UMBC. And so after like explaining a bunch of things in deep learning multiple times, I sort of like develop some like go-to like, well, okay, here's how I want to try and explain this, or here's how I tend to find people understand this better if I explain it this way. And then also just sort of like working for several years on like, oh, okay, here's sort of like the techniques that I end up using a lot, or the techniques people end up asking me a lot about, and common misconceptions around different techniques. So I sort of built up a decent amount of tribal knowledge on the subject area, and particularly not special tribal knowledge that only I know how deep learning works, but like how to teach people about it. And so I wanted to teach a class on deep learning at UMBC, and I didn't feel like there was any book that I super loved for the background level that I wanted to target. I felt like most of the things were either like very researcher oriented, like we're just going to go jump into a pool of Greek letters and swim around in the math for a bit, or no math at all. Let's just like talk about code and like just talk about like the libraries you use and coding these things up. And I don't love either of those sort of all-in approaches. I wanted something more in the middle. I want the code, I want to be practical, but I don't want it to be some obtuse black box. I want to peel back a bit and not necessarily do math, but like show the math and talk about it and how the math relates to the code and back and forth. Because that was important to me because this is a space that evolves so quickly that if you just learn the code, in 6 months, there's going to be some new paper about some technique. And if you don't have any ability to sort of like recognize the math from the paper and at least have a little bit of inclination on how would that impact my code, you'll be out of date pretty quick. And that's not good. And I also had this sort of particular mental model for like a linear path that I want to take on talking about different concepts in deep learning. So like one of the things that I tried to do in the book as like an example of just sort of like linearizing this a bit. Like a lot of materials will start with like, okay, let's learn Keras or PyTorch or whatever. And they start with like Atom as the optimizer or RMS prop or whatever. And so it's like, okay, we started training up this model, but there's like, what exactly is a convolution and what exactly is a linear layer? And like, why can't I just put like 2 linear layers in a row or 2 convolutions in a row? And like, what does Atom mean? And there's sort of a lot all there at once. And I find people who are learning don't fully realize how all the parts really interact with each other. And so I want to like separate that out and spread it out over the book. So like just starting with like, okay, let's just talk about like, how do we learn? We learn by optimization. That's the way that we're going to do it in this book. And so we're just talking about like stochastic gradient descent. And then like, okay, let's do just a linear model. We can do that inside of PyTorch. It doesn't have to be deep. It can be linear. Okay, let's do a linear model. Like, okay, now let's try and make a deep linear model. So we stick more linear models together and why is our result still linear? Well, that's where activation functions come in. And trying to sort of linearize all these different things that need to go into the process and introducing them in one at a time and showing or explaining why we're adding each of these things in one at a time so that people hopefully better understand not just doing it for like a rote memorization, but some intuition as to why it is this way, if that makes sense.
No, it does. And I think that one thing I really always admire is that you're building the resources based on how you teach and how you think about the problem, right? Inevitably, like people are going to think about problems different ways. And I think that it's important to say, hey, like, well, like, you know, someone might try the code first approach, someone might try the math first approach, and someone might find that, hey, like, neither of those work for me. This hybrid model works great. Someone might find that, oh, the code first approach, I really get it, and I can learn all the math later. But, you know, you're designing this around, okay, this is the most effective for how I'm teaching a course, but also how I'm, you know, how I learn this myself. And there's always going to be tremendous value in that. I mean, I generally learn better that way. So I usually like toy problem, learn math, go back, implement toy problem, like fool around with it, experiment with, you know, different optimizers, other like different ways to feature, to parameter tune, whatever that might be. And I figure out what each one of them does. And I try to, you know, do a lot of referencing back and forth. But to me, I also like the aspect that the idea that if you give advice more than once, make a blog post about it. I think you might have taken that to the extreme where it's if you're teaching something more than once, you know, write it down in a book. So I'm glad that you were able to integrate that and build something that I think is tremendously valuable to a lot of people.
I've definitely, it's definitely been a long time coming at this point. It's been a process, but it's been enjoyable, especially a lot of the feedback. There was one, so Manning has this like review process where they send out drafts to people that they like hope are the average like intended audience. And there's one person who wrote back on like one of the review things, just like my first thought was like, oh God, not another deep learning book. But then like I actually really liked it. So that and I've gotten a few emails from people now who have like said like they really appreciate the approach, and that means a lot to me. And there's definitely stuff like the recurrent neural networks sections of the book. Like I it probably took me 3 or 4 years to really grok what on earth a RNN or an LSTM actually was. Like I had used one and I had like written and like called code for it before, but like I had no idea what this weird concoction was, or like why was it recurrent? What did that mean? And it was this obtuseness to me. And so that was one of the ones where I like spent a lot of time like, how would I have liked this to have been told to me a decade ago?
Something there that I think is important for everyone who's learning data science or trying to get into this field to understand. I mean, you're clearly a very smart guy. You have a PhD in computer science. I've talked to other people. There's this guy, Josh Starmer, who has a StatQuest YouTube channel, and he's doing tutorials on statistics all the time. And in conversations with you and him, it's constantly like, yeah, I didn't understand this as well as I thought I did. It took me months to nail down this concept to be able to understand it well enough to teach it, but also, months for me to understand it to begin with, all of the different components of it. And it's not like people out there pick any of the more complex things up overnight. It's that like you have to put in the time, you have to do the due diligence. It's not just as simple as learning it and you do it. It's like you have to refresh your memory on these things. It's a continuing, ongoing process that is extremely time consuming. And for everyone, not just beginners. It's like even at the highest level, it's hard to keep all these things. I mean, for the course I'm teaching, I went through and I just did a high level overview of like, what is data science, or not getting into any of the algorithms or anything, just like, what is the field? Like what is a model? And it's 5 hours of class time to just talk about what the field is. That's without getting into any of the idiosyncrasies of the implementation or the algorithms or whatever that might be. So it's this huge thing.
And I will happily say, especially when people are like working on larger teams, like even for like me before I got my PhD, I was working with someone with a PhD. Like it was like kind of intimidating. Like, oh, they're a PhD in this. They must know so much. Like, PhD doesn't mean that I'm smarter or know more than anyone in particular. All it is certification that I am far more stubborn than the average person. That's all that really credentials me for, or any PhD holder for, really. There's tons of people who have bachelor's or master's. I have one coworker who like is super smart. I would pick him over almost anyone else for almost any project I would ever work on. And he doesn't even have any college education at all. He's got his high school degree and that's it. And he's freaking awesome. And it's really just like, how much time do you spend like actually tackling real problems and peeling them apart and figuring out how to solve them, that you get this depth. And anyone who does that is going to know way more than me or anyone else for whatever problem you're tackling.
Yeah, I mean, I love that. I think it's a function of time and that stubbornness. I think I read it somewhere. I was reading this book Grit a while ago, which is one of my new instant classic favorite ones. So yeah, I mean, those are all the questions I have. If there's any concluding remarks, anything you'd want to, any causes you care about, anything like that you want to mention, now's the time. Otherwise, I've really, really greatly enjoyed this interview, and I realize we went a bit over, so I apologize for that.
No worries at all. No particular concluding remarks, but if we're mentioning causes, I'll throw out Make-A-Wish Foundation is a really great charity. If people aren't familiar with it, basically helping kids who have terminal or life-threatening illnesses, and really just sort of like asking them like, what do you want, and trying to make that happen. And they're very emotional. If you participate and you can donate time or money, but if you donate time, it's very personal, but very rewarding. And a lot of kids, like I remember one of the first wishes that I helped with, like they just wanted a computer. Like that was their dream, was to have a computer. And so like we help them build like their own like custom computer from scratch and showed them how to build it and all that to try and sort of make it more than just giving them the computer they asked for. But seeing how much happier that can make those kids and their family, and just like relieving a whole world of stress, and really a reminder of the benefits and fortunes that we do have, and to pay them forward. So I'll throw that out there.
No, that's incredible. And so far, to the best of my knowledge, no one has asked to as their wish to speak to a data scientist or research scientist. So I'm sure we can make that possible if anyone is really nerding out. So
if that's anyone's wish, I'm happy to try and make that happen.
Perfect. I mean, I'm sure you try to make it happen even if it wasn't their wish. So
Yeah.
Awesome. Well, thank you so much for coming again. And again, I really enjoyed this, and I think that everyone's going to gain a tremendous amount of insight just across the whole spectrum: the PhDs, the malware detection, how data science is done across private versus public sector. Just all around fascinating call on my end.
Thank you so much for the time, and really enjoyed chatting with you. It was a lot of fun.